Hello everyone, I'm Daniel and I'm a senior .NET developer, trainer and Microsoft MVP on developer technologies since 2019. Before starting with my talk, let me tell you that you can use Scottish Summit 2021 hashtag for your social media to tweet or post if you like. This event is brought to you by the next sponsors: ScriptRunner, GlobalDQ, Proximo, Redspire, Agilysys, and Hitachi Solutions. Now, seriously, why another machine learning framework? In the world of data science and machine learning, Python programming language is making the rules. In addition to that, the existing frameworks like TensorFlow, Keras, Torch are not easy to integrate with .NET projects. I'm assuming you are a .NET developer. How many of you are happy to learn Python or other languages only to get some AI into your projects? The question is not to have or to not have another machine learning framework. The question is, what is the best choice for me as a .NET developer for writing machine learning code? If you are not new to ML.NET or another machine learning framework, you will agree with me that the process of building a machine learning model does not fit too well in a Visual Studio solution. I'm not talking about the production flow, where we are most probably consuming a pre-built model. I'm talking about experiencing with building a machine learning model. In this talk, we will explore a series of instruments for building a ML.NET machine learning model. But first, I have to make a disclaimer. I'm not a data scientist. I am trying to nail down the world of data science from a development perspective. When I first have to deal with machine learning, I was convinced that finding the right trainer is the hardest part. Totally wrong. As a proof, very soon, Model Builder was released. Model Builder is an intuitive graphical Visual Studio extension to build, train and deploy custom machine learning models. There is a CLI version 2, known as AutoML. But how this works? Model Builder, or AutoML, detects which is the best trainer for a specific machine learning task, by training each trainer from the catalog, by measuring the model quality in a limited time frame. This is a wonderful starting point for a beginner, but still we can improve a lot. So, to summarize, finding a good trainer is not a problem. The hardest part is to get everything ready for building the model. And that's preparing the data for your scenario. I even had some initial machine learning ideas which didn't fly for a simple reason. No data. You know what's interesting? The data is not the fuel. The data is the engine. Let's state a few things. Your machine learning model cannot be better than your dataset. Actually, a bad dataset drives to a bad machine learning model. Even more, it's better to have a good dataset than having the smartest algorithm. So be careful when preparing the data, because your data contains your biases. What happens if your data is not good enough? Well, please be careful. If you decide to save some time skipping data preparation, do not be surprised if you have to pay the price later. You will waste a lot of time and not in a productive way. But I think all this looks familiar to you. What about technical debt? Indeed, this is similar to technical debt, so I will call it data preparation debt. Let's see first what is a DataView. In ML.NET, data is represented as DataView, which is like a table with rows and columns. A DataView is an object being able to gracefully and efficiently handle high-dimensional data in large datasets, larger than main memory, thinks about tens of or hundreds of megabytes. Like relational database views, a data view is the result of computations over one or more base tables or other views. A data view is generally immutable and lazily evaluated, for good performance, of course. You can iterate through its elements. Data view has schema with collections of columns and rows, and it has metadata or annotations for extra information. And maybe the most beautiful thing, data view is composable. Why is this so important? It's important because everything in ML.NET, data loaders, transformers, trainers, estimators, predictors, savers are all working with data views. Now, because we are getting closer to jump on demo, let me introduce you the tool which will do our life easier. Jupyter Notebook. Jupyter Notebook is a very good REPL. REPL is the acronym for Read, Evaluate, Print, Loop. Jupyter Notebook is an instrument to play interactively with code and data and diagrams, and is very popular among the Python users. But with more than 6 million .NET developers in the world, Jupyter Notebook with .NET kernel is very welcome. Some benefits. You can integrate documents with code and diagrams. Is interactive. Is working with C# scripting. Take care because you cannot use namespaces, and that's because using keyword has double meaning in C#. Bad idea. Jupyter Notebook is polyglot. If you use Jupyter Notebook with Visual Studio Code Insider, you benefit from IntelliSense, and the kernel is up to date to the latest version. .NET developers can run on-premise machine learning scenarios with Jupyter Notebooks using C#, F# or PowerShell kernels in a web browser or in, as I said before, in Visual Studio Code Insider Edition for now. Jupyter Notebooks supports commands like interrogating the system for version, loading dependencies and libraries, loading CSX files, C# scripting files, examine the memory for variables and their types, switching the context for various languages. It's polyglot, as I said before. That means it's capable of mixing multiple languages in the same cell, and it's capable of exchanging data by using the same process. This is possible. In a Jupyter Notebook, we can still use console write line to print data, but we will love display command since it's able to print text, HTML, or SVN, or charts. Display command is built on PocketView API. Think about PocketView API like a library consisting of C# helpers for rendering HTML code. I can see an analogy here with Razor. Of course, we don't understand much looking at the tabular data, but Jupyter Notebook brings up some great diagram types with XPLOT Plotly data visualization library, being able to aggregate the data in a more useful way. XPLOT is a cross-platform data visualization package built for F# language primarily, and it's powered by popular JavaScript charting libraries. But what is a DataFrame? DataFrame is an efficient way of visualizing data. Actually, DataFrame is part of Microsoft Data Analysis Library. If you are familiar with Python, you will recognize Pandas because DataFrame is pretty similar to Pandas. DataFrame is an immutable in-memory representation of structured data stored as collections of columns and rows. We said the same about DataView, but DataFrame is not lazy loading its data. For that reason, we have to take care on large data. DataFrame supports a series of operations or computations, joins, merges. It's handling missing values. It's adding or deleting columns or rows. The printing format can be improved using object formaters and PocketView API. For example, we can use object formatter to render more complex data in a friendlier way. Okay, now we know what's a data frame, but let's see what benefits it brings. Basic question about the dataset. How many observations and features? What data types do we have? Are they numeric? Are categorical? Which is the label feature? The purpose of displaying examples from the dataset is not to perform rigorous analysis. Instead, it's to get a qualitative feel for the dataset. Do the columns and values make sense? Are the values on the right scale? Is missing data going to be a problem? The usual flow building a machine learning model is something like this: load data, visualize, analyze, prepare, build model, and predict data. We can think about skipping a few steps here, like visualize and analyze data, if we are beginners. But in that way, we will not understand what we are doing. We need to visualize data in order to analyze it, and eventually to prepare the data accordingly. Now, first things first, loading the data. Observations are collections of lines consisting of features or readings. The supervised learning needs a special feature which serves as target feature or label. My use case used for the demo is supervised learning. More exactly is multi-classification. Therefore, my label will be a category. Let's take a look on the source column. The categories are flashlight, day, infrared, and lighter. But let's see how we can load some data from different sources. ML.NET is able to consume data from SQL databases, from CSV and TSV files, or from images or binary data. Please remember that everything, data loaders, transformers, savers, trainers, are all working with DataViews, because DataView is the native type that ML.NET is using to manipulate data. In order to analyze data, we have to visualize it. By using load from text file, we load data from one or more external CSV files. Now we have data in DataView, but DataView is lazy loaded. How can we visualize it? Well, one way is to convert it to an IEnumerable and to a list. We can take a look at our data using collections, but that's not very useful since it's lazy loaded. Manipulating data with DataFrame is very useful, but eventually we have to move it in a DataView object. We can do that in two steps. First, convert it into a collection and then load it into the DataView. Another way to inspect data is to use Data Debugger Preview, which is recommended only for debugging. Hence the name, Data Debugger Preview. Write CSV is not part of the library, but is something what we naturally need in order to persist the data frame changes. This is something what I have contributed on GitHub repository of Microsoft Data Analysis Library and will be probably included in the next release of Microsoft Data Analysis. Let's analyze the dataset which I used for demo. Let's suppose we have a system able to measure temperature, luminosity, infrared, distance, and the created data. And we have a dataset consisting of 1000 of observations. How much data is enough? Well, it comes with the experience. But keep in mind, you have more categories or classes, you need more data. You need more precision, you need more data. Too much data never hurts, as long as it's good data. These observations are labeled. That means we have a feature called source for these readings for every observation in the dataset. Actually, the source from the sensors is generating these observations. These sources of data are lighter, flashlight, daylight, and infrared. Let me exemplify. We have a data set with a set of sensors reading from an IoT device, and we want to predict the source of these readings. Giving 20 Celsius degrees, 19 luminosity, 0 infrared, and 100 centimeters. What is the source of this observation? Maybe it's a flashlight, right? Data from sensors can be calibrated or uncalibrated. Calibrated means the data are scaled in a specific range, like 0 to 100. But that's depending on the sensor's type. We have here 5-6 columns, and we might find it pretty hard to understand every line and why it's labeled with a label or another. Now let's think a little about 10 or 20 features. It becomes soon impossible to discriminate between the categories from so many analytical data. Our brain is simply not built to identify large-scale analytical data. Why is that? Because the combinations of all the features are equal to 2 by n. We have 2 by n if-else statements. For 4 features, that's 16. But what about if we add another 3 features? Well, that's 2 by 7, which is 128. And that's not all. Let's suppose we are indoor, in a room. Well, bad news. Indoor, the luminosity is different than outdoor. The temperature, the same. Move your sensors outside and your code will fail because the system is not calibrated for outdoor. And then you have to redefine all your thresholds and maybe even change the algorithm in a few places. But doing all this with machine learning, well, it's just wonderful because we can get another model in minutes. And we can train on different datasets, outdoor or indoor. Actually, the larger is the number of the features, the better to choose machine learning. Let's see how we can analyze our data. Read some data from CSV and split that data in training and testing datasets. Create an enumerable collection. Remember, data views are lazy loaded and they are loading when we call the fit method that triggers the model training. So, let's create an enumerable collection. We can visualize data using different diagram types: categorical distribution, numerical distribution, box plot segmentation, and correlation metrics. Let's talk a little about all these different ways of looking at data. With numerical distribution, we look at the numbers for distributions that are unexpected or for potential outliers that don't make sense, or for features that should be binary, or for boundaries that don't make sense, or potential measurement errors. On the other side, with categorical distribution, we look at the categories or classes. Bar plots are good to identify the distribution ranges for the categories. we can identify easily the sparse classes. The sparse classes are classes that have a very small number of observations. And maybe we can fusion two small categories into a larger one, if it makes sense. With XPLOT segmentation, we can extract valuable information like this. The median bar from distance feature is much higher comparing to the other features. Then, the min-max values from temperature and from infrared features are not uniformly distributed. Temperature feature has many outliers. We can use this information later to improve the model's accuracy. But now, there is one other thing which doesn't look right. Some features look heavier than others. Take a look at the distance. Its range is from 0 to 400. In the same time, luminosity and infrared, it's from 0 to 100. The impact will not be the same. Let's see what happens if we try to bring all of them to the same scale, or to normalize them. Well, now the features are normalized. Please be aware that some trainers are normalizing themselves. We don't have to normalize again. Other trainers are not, so it's up to us to decide if we need or need not to normalize our data. Now another question arises. Do we really need all these features? Generally speaking, the more features we have, the better. But this is increasing the dimensionality of our model. Therefore, there is a direct impact on the model performance, like training time and prediction time. Correlation matrix is a wonderful instrument to analyze this. It is possible that some features are strongly correlated, therefore redundant, but not the case here. With correlation matrix, we can measure the correlation between the features like it follows. Near -1 or 1 indicates a strong relationship. Closer to 0 indicates a weak relationship. 0 indicates no relationship. For example, our most correlated feature on this diagram is distance and infrared. And the temperature feature seems to be the most uncorrelated feature compared with the other features. What is the outcome of such analysis? Well, as I said, the strongly correlated features do not convey extra information, therefore they can be removed. It's not the case here, because we don't have strongly correlated features in our demo, but we can imagine reading the temperature from two sensors which are very close. The temperature will be pretty much the same for both sensors, resulting in highly correlated features. But we can think of something which is not so obvious, like temperature in infrared for short distances. Again, this is not the case here since our demo is working with distance. We are done with data visualization and analysis, and we have now important insights about our data, so we can proceed to data preparation. Data preparation means, among other things, data filtering or cleaning, like finding and removing duplicate data and irrelevant data, or like fixing structural errors, or like fixing typos or capitalization. Then it's filtering unwanted outliers. We may have experimental errors, but not all outliers are bad. For some systems, extreme measurements are natural, but for other systems they are all errors. For example, if we have calibrated sensors which gets values in range 0 to 100, a value like 130 is a measurement error. Now, cleaning the data. Do we have large enough datasets? Well, think again, because we have bad readings, incomplete, inconsistent, altered data, which are garbage. That's bad data and we don't need it. Then the left data had to be split into parts, training data and testing data. We put aside the testing data and we don't use it at all in the training process. We don't want to test the model with the same data we used to training it, right? Now let's take a look over the pipelines. The pre-processing pipeline is consisting of data loaders and transformations like converters or key value mappers or concatenators, column operations, time series transformations or text transformations, image transformations, normalizers, and more. The training pipeline is consisting of an estimator, which is a trainer from the catalog. And the post-processing pipeline is not so busy, but we can have here value key mappers. We call fit method on the model builder pipeline to get our model built. We can save it for later use, but most probably we didn't get our best shot, so we measure the quality of the model. Cross-validation is done for the model against the training dataset. And we can measure the quality by analyzing the metrics and the confusion metrics. On the other side, evaluation is done against the testing dataset, not training dataset as it was for validation. They look pretty similar, but not operate on the same dataset. We can measure the quality by analyzing the metrics and the confusion metrics. In addition, we can measure the permutation feature importance. Let's talk about all these metrics in the next slides. Cross-validation is a useful technique for machine learning applications. It helps estimate the variance of the model quality from one run to another and also eliminates the need to extract a separate test set for evaluation. We measure the standard deviation and confidence interval for micro accuracy, macro accuracy, and logarithmic loss. But how it works? Cross-validate performs the following operations. It partitions the data into a number of partitions equal to a specified value called number of folds. The result of each partition is a trained test data object. A model is trained on each of the partitions using the specified machine learning algorithm on the training dataset. Each model's performance evaluated using the evaluate method on the test dataset. A set of metrics of the model is returned for each of the partitions. The metrics are calculated for each fold and they are aggregated showing the average, standard deviation, and confidence interval. Now let's evaluate the model. By evaluating the model, we get micro and macro accuracy and logarithmic loss, as it was for cross-validation. But we get the confusion metrics as well. Well, after getting a model, the first thing to concern about should be the model performance, and the confusion metrics is an excellent performance measurement for machine learning classification. Using the testing dataset, we can make predictions and compare the predicted results to the actual results. In the previous diagram, we can see the infrared class was predicted correctly as infrared for 40 times and incorrectly as flashlight for 5 times, and the lighter 1 time, resulting in a 0.8696 precision rate. Another useful instrument is the permutation feature importance. PFI computes the importance score for each feature by random permutation of the feature, resulting in more or less important features. By adding a correlated feature can decrease the importance of the associated feature. You will occasionally see negative values for permutations importances. In those cases, the predictions on the shuffled or noisy data happen to be more accurate than the real data. This happens when the feature didn't matter or should have had an importance close to zero, but random chance caused the predictions on shuffled data to be more accurate. This is more common with small datasets, like the one in this example, because there is more room for luck or for chance. Here, in our diagram, the humidity and PIR features seem to have a very low score. Dropping them will not result in a significant reduction in our model performance. Having a model, either by loading a previous saved model or by having already a generated one in memory, we can create a prediction engine. We have to read a new observation to pass it to the model. The prediction comes out as output. Output is a data which in fact is a class or a category with an associated score. Let's switch to Visual Studio Code Insider Edition. We have here a sample. This is a trivial version. We are initializing the ML context. Let's wait a little. So it's installing. And then we are loading the data, splitting into datasets, training and testing dataset. Then we are proceeding to building the training pipeline. Here we are concatenating the features. As you can see, we are using all the features here. 6 features, we are using all of them. We will realize later we don't need all of them because they are simply not relevant for our model. But for now, we are running all. And we are calling LightGBM, which is a trainer for multi-classification. By calling fit method against the training dataset, we are actually building the machine learning model. Okay, now we have the machine learning model. And let's measure the quality of the model by calling a transformation against the testing dataset. And then we are calling evaluate these predictions in order to measure the quality of the model. Okay, we can see now the micro accuracy, it's 9130. The macro accuracy, it's 9078. And we will see if we can do better. But let's predict some data, because this is what we want in the end. So, having 32 degrees, this is the temperature, right? Luminosity 22, this is a percentage. And then it's infrared 0, distance 20 centimeters. And the rest. Definitely this looks like a flashlight, because we have some luminosity, not too much temperature, and no infrared. It's cold energy, cold light. Let's call this and check. Yes, it's a flashlight. Probability 85%. But let's increase or let's decrease the luminosity. Now I'm expecting maybe, yes, it's daylight because it's not so bright. Let's put back this luminosity. Let's play with temperature. Let's put 132 and some infrared. Now we are expecting something hot. It's a lighter. If we don't have temperature at all, that means it's it's not hot, but still we have radiation. Then it's infrared. So it works, but of course we can do better. This is a simple use case, but we always need to improve the quality of the model. And we will see how we can do that. Now let's visualize some data. Let's load the data analysis dependencies. And then let's load the data frame by calling load CSV. As we can see, the data doesn't show very nice. I mean, it's not easy to read. Definitely we can do better. And for that, we will use object formatter, which is specifically right for DataFrame class. The code is not very little because I have implemented myself a navigation system below the data. And then I'm calling the register for DataFrame. Okay, let's just run this, okay? It will do the job. It looks much better and we can navigate through all dataset. But please do not load here 1 million records because it will freeze maybe. This is something which I have contributed to Microsoft Analysis, Data Analysis Library. When we have the data, we might need to modify it. For example, we can call here lots of methods to modify the data, to manipulate the data. For example, we can call some operators, or we can clone some columns, or drop the columns, or fill empty values. We do a lot of things. But at the end, we need to save this. Well, for now, DataFrame doesn't have a nice way to save the data into a CSV, back into a CSV file. So for that I have written write CSV method, which is another thing which I have contributed to GitHub, open source repository for Microsoft Data Analysis. I will call this, and then we can simply write the new content. Let's presume we have modified something. We can save it in an external, in another CSV file. And then we can load this file for our model to have a new data set. Now let's analyze the data. Let's initialize the context. And then let's load some data, split it in two data sets as before. And now we are extracting the features in order to show them in some diagrams. For example, we can use numerical distribution. Okay, they are showing in the same time, all of them, they are all of them here, but let's deactivate. Now we have temperature. We can tell about temperature. The most values are in this range from 0 to 50, more or less, to 40. And very few are higher. This is a good way to see how your data is distributed. Then let's go further to see some categorical distribution. For example, we have here the categories: daylight, infrared, flashlight, and lighter. We can tell they are pretty balanced. and then it's the same thing but for testing data. We have to check them as well. Uncalibrated data will not create a good model. And then it's the box plot segmentation. This is my favorite. We have here some values. Nevertheless, it's obvious distance. It has greater impact because it's spread over a larger range, and these analytical values are all creating an impact on the final model. We have some outliers here for distance, more outliers for temperature, but they are okay. I mean, they are valid. We have almost nothing for PIR or humidity, but this is our data. And then let's see the correlation metrics to see how correlated are our data. Okay, for example, temperature and infrared, they are not very correlated because the distance has an important impact on them. Obviously, we don't have here too much correlated features, so we will not take a decision like removing from this perspective, removing one of these. But if we have highly correlated or highly uncorrelated features, we may decide to remove one of them. Let's prepare some data. Now we have important insights about our data. So let's go further. Yeah, I didn't wait enough for this to load and I got errors. So we can see here the box plot segmentation, but now I have normalized. I have called here the normalizing. Okay, it's right here, see? And then let's build a training pipeline, and then let's check the permutation feature importance. Well, this is more helpful because we can tell humidity and PIR are not bringing too much value to our model because they don't have an impact, an importance. They are not very well, they can simply be missing from here. The confusion matrix, we can tell here, for example, the flashlight was predicted as a flashlight in 70 times. It was predicted as infrared, mistakenly of course, one time, as a daylight 2 times, and the lighter as a lighter 2 times. So now we can tell this is not perfect, right? The recall rate is 0.93. Now we have enough information in order to decide which feature to keep or not. Let's run this again. Train the pipeline. We have noticed PIR and humidity is not bringing value to our model, so we will run without those two. We will keep temperature, luminosity, infrared, and distance. And let's check now the quality of our model. Well, the precision increased. Let me check again. We had 9130 and 9078. Now we have 9230 and 9181. Well, let's check what happens if we get rid of the distance 2. Let's evaluate again. Oh, and I see it increased even more. Now we have 93 for both. That means if we keep the temperature, the luminosity and infrared, our model will perform better, at least for this data set. Ideally, we need more values, but it seems like if we keep temperature, luminosity and infrared, the quality of our model is the best. Well, this is a result of our analysis and preparation, so we managed to increase the quality of our model by using these instruments. Thank you very much for watching me.